that we are in the middle of the week. I suppose we are kind of getting readjusted now back to the pattern of getting up and going to classes. Like I said on Monday, I hope you had a restful spring break and you're ready to jump back into it, because we are at the longest chapter of the semester. And so I want to dive right back in where we left off, giving you the same hopefully helpful hint that, again, you need to remember what we did for translational motion, because we're going to take that same logic but apply it to rotational motion. And you'll see that again more today. And so I'm going to try to finish up our lecture on our material and then use the second hour to do examples. We'll see how far that gets us. I suppose it wouldn't surprise me if examples then flowed into next Monday. It's just too much to try to do all of this in 1 week. And we actually have a little bit of leeway there, because following this chapter, chapter 11, is one of the shortest chapters of the semester. Not exactly an easy chapter, though. I don't want to use that to scare you, but to give you kind of a heads up. It's not necessarily easy, but at least it is short. There's not that much material in it, and it is, again, more on rotations. So let me come over here. I had this big chart. Maybe I'll put it back over here to the same place on the board here. We had a list here of translational quantities and definitions and ideas, and we were trying to extend that to rotational quantities to get you to see the idea that everything we've done, including conservation of energy where we left off, is part of the process, and now we have rotational kinetic energy. And so we had a full chart, and then actually we started a second one, you might remember. Let me just kind of pick up where we left off. We had this, that in translational motion we would have this thing called inertia or mass. It's resistance to change its motion. The analogy to that is the rotational inertia, which we said was a little more complicated, and we spent a while working on it, and we're going to spend even more time today working on it, because again, I think this is one of the hardest parts of rotation, that and torque, and those are the two biggies we will wrap up this chapter with. And so this moment of inertia, would have units then of a kilogram and a meter squared, as we said last time. And what I was trying to emphasize was that this is like that, only it is not just mass, but it is where that mass is located. And so where I spent a lot of time was trying to illustrate that it wasn't just the mass that defines how difficult or easy it is to get something to rotate. It's also where that mass is. So I thought I would remind you of that and then show you this quick demonstration. Here's a good example. I got a small weight. It's put on a string that is obviously wrapped around a pulley. If I release the mechanism, you'll see that the weight tends to make this rotate. And so this is definitely a rotational problem. And in fact, it looks like, there we go. And so it pulls down and makes this turn. And I just want to do it a couple times here to kind of give you an idea of how fast, or you might say slow, this thing unwinds. But I want to ask this question. What do you think might happen if I were to remove these 4 kilograms and let it go? Yeah, and I hope you can see that it does unwind, and it looks like this doesn't really want to unwind as fast as I'd like it to, or as smoothly as I'd like it to. But I'm hoping that this isn't a big surprise. This unwinds much quicker than it did when those weights were on. And of course, I would say, well, it has less rotational inertia, less moment of inertia. And I would say that just because it has less weights. However, the real picture I want to show you is, let's put those back on here. Let's just take a mental look at it again. So there it is, unwinding. What do you think might happen if I do not change the weights, but I place the weights in a different location? And this, I hope, is a good illustration of what we mean by the moment of inertia. And that is, this is harder to get it to rotate. Not because there are more weights on here and that it has more mass, but it's the distribution of that mass. Where is it located? And so if I was doing a calculation, which we will here in just a second, then this mass is now located further out, and you end up with a bigger number here. And that's what I'm trying to illustrate, that this number, like this one, is an indication of how easy or hard it is to get something to rotate. But unlike the translational motion, where it has just to do with mass, this has to do with mass and the positioning of that mass, the distribution of that mass. And so that, I hope, illustrates it well. You might remember that last time we used this wooden disc and this metal hoop in a discussion and said, even though they have the same radius and even though they have the same mass, do you think they have the same moment of inertia? And of course you guys told me no, you didn't. And I asked which one was either bigger or smaller. I think bigger. And you guys told me the hoop, right? Logic being that all the mass would be at the end. I said if you were to drop them versus rolling them, there would be a different speed. Let's run through that real quickly again. This was the illustration of kinetic energy. That is, when we did translational motion, we had this 1/2 mv squared. Now, dealing with rotational motion, we have a 1/2 I omega squared. And as we showed last time, it would still be in measures of joules. But we did this little problem and we said, all right, if you had an object up on the hill, and so up here, and you measure things from its center of mass, and so let me call this y equals to 0. And so if the object starts with an initial height and I apply my conservation of energy, I would say initial energy is equal to final energy. And what I was trying to show you on Monday, and we'll show you one more time here, as I go to work this one out, I would put in all the energies before, and so if I start at the top at rest, there is no other kinetic energy, there's no translational, there's no rotational. But what is different or new for this chapter is when it gets to the bottom of the hill, that object will not only be translating, but it'll also be rotating. And so our argument was if you just dropped it straight down, there would be no rotation, and its translational speed would be very, very fast. On the other hand, if you let it roll down, by the time it got down to the bottom, it should have some of its energy in rotational kinetic energy, and therefore less energy is available for translational energy, and so the object should be going a little bit slower. How much slower would depend upon the inertia of each one. And as you pointed out, the hoop has more inertia than the disk, and so we did a couple of steps, and it's probably worth repeating them here again. The first thing we did was to factor out a 1/2 m, so that this then became an I over an m, and then this was our v squared over our r squared. If we continue to factor out the 1/2 m, and then we write this as 1 plus I over mr squared v squared, and we cancel an m on each side and solve for v, we left off with 2gy initial height on the top, and then on the bottom was 1 plus I m over r squared. And so I wanted to put that back here on the board. You can see in the math then that clearly when you throw in this extra ability for it to rotate, then this number downstairs is greater than 1. When we dropped it straight away, without that term, we said the speed would be the square root of 2gy initial. So clearly anything that is now going to rotate must be going slower at the bottom of the hill. And so I thought it might be nice to actually set that up today. And so when we had left off, and maybe I'll have to maybe I'll have to leave it back there with my incline. You guys can see the end of the track there. But if I were to start this one here and let it roll down, or start this one here and let it roll down, or this one, which doesn't roll, although the wheels roll, but those are small compared to the whole object. But if I take this one and let it go down, then let's race all of these. And I claim that the one that doesn't roll then has all of its energy in translational kinetic, and therefore is going faster than anything that is going to roll. And so if I were to race the cart and the disc and let it go, other than falling off the track, this one clearly wins. If I were to race this car and the hoop and let it go, again, clearly this one wins. Now these guys obviously go a little slower, but as you pointed out, this one probably has a larger moment of inertia than this one. Hence, more of its energy has to go into rotation, so less is available for translation. And I would then expect this hoop to go a little bit slower than the disc. And sure enough, it does go, the hoop does go slower. Let's put some numbers in here now. Let's see if we can actually then do a calculation here and calculate. For example, what is the moment of inertia of this hoop? This is the idea of calculating the moment of inertia. So let me draw that up here. Let's say, okay, what would it look like for a hoop or a ring, whichever word you want to put there. And I think sometimes your author uses ring and sometimes he uses hoop. But if I were to say, what is I for a hoop or a ring? Well, it's the sum of MI/RI squared. Fortunately for us, we're really good at calculus, or we're getting good at calculus. How's that? Because when you add these up, it's not, say, as simple as just adding two objects. In fact, let me sidetrack for a moment. If I were to do this one and spin it, and I say I wanted to know the kinetic energy of this spinning system, I would need to know the moment of inertia of those two objects. And if you remember this one from last chapter, this one we said had one object that had 3 times the mass of the other object. And that the string was tied in such a way that this is 1/4 of the length, and this is then 3/4 of the length. In fact, we calculated that was the center of mass, and so we tied the string here at the center of mass. And let me not go back and repeat the proof that that is the center of mass, but I'll tell you that is the center of mass. And so if this thing was spinning, this would be a fairly easy, I think, calculation. I've got 2 objects. And of course, just like last chapter, I'm ignoring the metal rod that is connecting the 2. But if I were to ask what is the moment of inertia of this, I would say, well, it is the sum MI/RI squared. And I would have 2 objects. Let's measure here from that center of mass. So I would say my first object has a mass of 3m, and it is a distance of 1/4 of the length of the rod. And so that would be my first term. And my second term would be m, and it would be at 3/4 the length of the rod. And so there's how I would get the moment of inertia of this one. Then, of course, you can see that 1/4 squared is a 16th. So this is 3/16 ml squared. And this is 9/16 ml squared. So each one contributes to the ease or difficulty of getting it to rotate. Each one has a moment of inertia. And in this case, we can now add them together. You can see, though, before I add them together, that it is this weight out here that contributes the most to the moment of inertia. By far more, right? This 9 is 3 times more than this one. So if this thing is hard to rotate, it is mostly hard to rotate because of that one there, not because of this one. I know this one has more mass, but it is closer in. And that's why the moment of inertia is a bit more complicated. It's not just how much mass do you have, but where is that mass located? Of course, now when I add them together, I take a 9 and a 3, that makes a 12. 12/16 L squared reduces to 3/4 mL squared. And so the easiest one to do, I think a little bit easier than this hoop, is to say, what if I just had 2 objects? I can then just find the mass of each object, the position of each object, do the arithmetic, and come up with the answer. So I thought we would start with that one. That's the easy one to get the moment of inertia. But what about the ring? How are we going to get this one? Maybe it's worth drawing a picture. I mean, there's the ring. There's the center of the ring. This says add up all the little pieces. Well, what are the little pieces? Right, and this is where calculus is going to come in, right? This is why you learn things called an integral. You could take this and chop it into an infinite number of pieces. And so that's what I'm really asking you to do, is to chop it up into fine little pieces and add them together. Use your knowledge of calculus here. So I'm going to chop, 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 and I won't actually put an infinite number of chops up here. But hopefully that will come across as a very small piece of mass. And so let's call that little mass dm. Right? Now, I suppose if it helps, maybe I should call it delta m and let delta m approach 0. Would that look a little better in terms of your calculus? Because what that is saying then is, knowing calculus, I can then write that summation to look like this. And so what does my calculus tell me? Does this look familiar at all? Yeah, what's this become? An integral. An integral of what, though?
Ri squared dm.
Good. It is r squared, and I'll go ahead and drop the I, but you notice it was a dm, not a dr? And that seems to be the common mistake, and rightfully so. You guys are fairly new at your calculus. But remember, the dm or the dx or the dr, whatever it is in your calculus, was what is the piece that is getting small. And I know it's very tempting because you've done so much calculus and you always have a dx to call this a dx or something. And so this looks perhaps a little different than your Calculus 150 class. But let me assure you, it is not. When you did your calculus and you had that little dx, please remember that x didn't necessarily mean the horizontal position. That x meant a variable, something that was getting small. And in this case, what is getting small is the chunk of mass. You could even say the size of that mass. So we might change our dm into a size here in a second if we need to. But please remember, it is not dr that is getting small. Let me look carefully. What does r mean in this equation again? Yeah, it's the distance the mass is from the rotating point. So if I have something that looks like this, and I want it to rotate, I don't want the radius of this to go to 0. Then I don't have a hoop anymore. I just got a little point. That's not the idea of my calculus. I'm not trying to take the limit as r goes to 0. I'm trying to take the limit as the chunks of mass get smaller. That means the mass itself goes to 0, not the position of it. Fair enough? And so for some reason, on this homework and on the next test, I get a lot of confusion on this. When students do their calculation, they seem to want to take r and send it to 0. That is not what is going to 0. R is the position of them. I would agree that the size of the mass is going to 0, yes, which also means the mass is going to 0, but not the position of it. So we can change then what would be an algebra notation to a calculus notation. And so let me put a second equation up here, one that really is our beginning definition, but one that allows you to go beyond just adding up the masses, which is kind of what we did in, well, I'll say 102, but I don't even think in 102 we kind of took it that far. I'm not sure how Dr. Kelly did it, but I know the book, and I know when I did it, I don't necessarily have the students do any of these calculations. I suppose that's what makes chapter 10 kind of a rude awakening for students when they come here. They're like, okay, a lot of this stuff is new. Talked about it in concept, but not in calculation. And definitely did not do any calculus in 102. So that being said, let's come back to the hoop. That, okay, here's what I'm trying to do for this hoop. I'm trying to find what is the moment of inertia of the hoop. And I realized that they're not just individual masses, it's a whole continuum of them. So I've got to break it down into infinitesimal pieces and then apply my calculus. And you'll see here in a second why I picked the hoop first. This is probably the easiest of all the calculus you could ever do. Because what would you say about R here? Yeah. I picked the hoop because all the mass is at the same distance r. And so the first thing I would do is to pull the R out in front and even maybe change its symbol from a little r to a capital R, saying that this capital R is actually the radius of the hoop. Whereas back here, the little r didn't necessarily mean the radius of the hoop. The little r meant the position of that chunk of mass. But since it's a hoop, it's all at the rim anyways. That is not the case for a disk, as we will soon see. But this one, it is. In fact, it then makes my calculus really easy to do. Because what's this integral? Yeah, doesn't that just mean the sum of all the masses? So let's just kind of read the mathematics as opposed to doing the mathematics. It is saying add up that chunk and that chunk and that chunk and that chunk. And if you were to add up all these chunks of masses, what would you get? The total mass of the hoop. And so here's my ring slash hoop, and I'm just going to put capital M, capital R squared, put a little box around it and say, okay, there is my first calculation for the moment of inertia. And if I use that back over here and say, okay, so what is the velocity of the hoop? It would be a 2 times the g times y initial divided by 1 plus. And in the top, I'll put my capital M R squared. Now on the bottom, I have a little m and a little r squared, although they might be the same thing. Let's talk about where those came from, right? The m back here was the whole mass. So, even though I've kind of changed my notation back over here, because over here I was using little m for the whole mass, I kind of got away from that here because here I was using little m for little chunks. And so to emphasize that this sum of the little chunks is the total mass, I used a capital M. But I hope that didn't confuse you back in this equation. Those are really the same m's. Okay. And then likewise, back here in this part of the problem, I had used a lowercase r. But lowercase r was the radius of that hoop. I kind of changed over here because this lowercase r I was really using back here as the location of the chunk of mass, which may or may not be at the total radius of the object, but it is for the hoop anyways. And so that's why I changed it in notation from a little r to a capital R here. And so this is the total radius, but that's what was meant here. So in this case, they cancel off. They don't cancel off in every case. This is one of these ideas, probably more than anything else, is you really got to be reading the math here, understanding it. You can't just put in the numbers and plug and chug and say, oh yeah, I'll memorize this equation. I see an I on the test, I'll plug it in. This is the place where you can really foul yourself up if you're not understanding the concepts and you're not reading the math. You got to do far more than just do the math. It's been a while since I said it, so maybe it's worth saying it again. This is not a math class. Don't treat it as just, hey, I'll just memorize a bunch of formulas, I'll punch them in, I'll plug and chug, and I'll get the answer. And there's times where that will work. You'll even get a certain amount of partial credit for that. And you'll do okay. And you'll get an okay grade. And you'll transfer to an okay school. And you'll make an okay salary with an okay career. But I hope you'll do better than that. And I hope you'll thrive and really understand the details, which will open the door to actually start to be creative in your thinking process and begin to invent things and do things that have never done before. And that really is the big difference in both science and engineering, is that there's not a formula already done. If the formula is already there, then somebody else has already done it before you. You got to come up with the formula yourself, and it has to be based upon things that are possible because of the laws of physics. And so that's why you learn about all these laws of physics and the law of conservation of energy and the law of conservation of momentum. It tells us what we can and cannot do. And then from that we can be creative and do something that hasn't done before and take that next step, the better product. And that's, anyways, this idea. Well, those all cancel off, so eventually this simplifies to 1 plus 1, that's a 2, canceling with that 2. And so I would get this formula here for the velocity of this hoop or this ring at the bottom of the hill. And clearly that number is definitely less than that number by 41%, since the square root of 2 is 1.41. So I would think that anything not rolling down the hill, like this cart, would end up going faster than this hoop by 41%. Let's continue with this. Let me, I don't want to lose too much of this. Why don't I take this off the board here. And then I think we'll have a little bit of room on the other side. But what about the disk? Or, if you like, I could even call it a cylinder. Usually things that are this shape, we call them a disk. If they tend to be kind of short and fat, they're a disk. But if it was more like this, where it is taller than it is wide, we tend to call those cylinders. But I think you would agree the layout is still the same, and so whatever I calculate here and how I calculate the moment of inertia for a disk would certainly be the same that I would calculate for a cylinder. And so let's do the disk, or cylinder if you would like. All right, how are we going to do this one? This one looks a little harder. Yeah, I mean, I guess technically it's that, right? So I would have to take this disk and I would have to add that chunk and that chunk and that chunk and that chunk and that chunk. And so I might go all the way around a circle, which is essentially a hoop, right? And then once I get a hoop, then I would go out a little bit and do another hoop and another hoop. In fact, since I already did the hoop, why don't I take advantage of that? I mean, let's think of it this way. Here's going to be my calculation. I'll do a hoop, and another hoop, and another hoop, and another hoop. So this first part would be adding up to get a hoop, and then I would add a bunch of hoops. Since I already did the hoop, will it be okay if I just kind of write it this way? See, I already did the hoop. So why don't I take advantage of that? And so I'm going to add up my hoop. Now, let me make it real clear here, because this can get kind of confusing. There's a bunch of m's floating around here. I would say there's really kind of 3 m's going on here. I mean, 1 m, I would say, is going to be what is the whole mass of this disk. But that is not this m. What is this m?
Mass of that mass.
It's the mass at a certain radius. It's the mass of a hoop. So maybe to make it a little clearer, I'll actually put hoop underneath it here to say, look, this is not the whole mass of this cylinder. In fact, what did I mean by this little mass back here? This is a different variable, if you will. What would this one mean? Yeah, that was the mass of a little bit of chunk that was back here. That was a small piece that when we added all the pieces around in the ring or in the hoop, we got the whole hoop. And so I just want to make it clear, because there's so many m's floating around here, that if you're not reading the math, you're going to get lost here. Okay? And so maybe to make it clear, since I only have one mass in the equation here so far, I want to make it real clear what that m is. That m is the mass of a ring. It is not the total mass of this, and it is not that original mass, which comes from the definition of what we mean by a moment of inertia, which is the mass of a little chunk. It's not that either. Okay? And so, just hopefully got that clear. Yeah.
So if we're able to use the hoop as like our infinite hoop over there,
yeah.
does that mean that that hoop's infinitely thin?
Well, okay, yeah. Now, I guess I should be real careful here. Notice here that in this derivation of the hoop, I said all the mass was at the same radius. So what am I really saying at that point? Yeah, what you just said. It's infinitely thin, right? So I'm going to add up an infinitely thin amount of hoops.
I guess what I'm getting at is that an approximation? Because our hoop actually does have...
Oh, yeah, good point. Good point. So this derivation is an infinitely thin hoop. No hoop is actually infinitely thin. It obviously has an inner radius and an outer radius. And we'll do the disk, but when we're done with the disk, we'll jump back to what you said is, what if I had something that, you know, just had a hole cut out, so there would be an inner radius and an outer radius. I don't have anything up here like that. You'll see it in the lab next Monday. We have when they give it some thickness, we call that an annular ring. So it's not a ring, has a little thickness to it. Okay, good. So you're seeing that here. And again, that's why all these little derivations are so important that you go through and understand them. You can't just get to the end and say, okay, well, here's the result. You got to know, what do they mean each step along the way? And therefore, when is it valid and when is it invalid? I'll even do like we did last time. Why don't we take the limits as the hoop gets infinitely thin, and then add up our hoops, right? And so there's our calculus again, right? And I think this one's a little bit harder. The logic is still the same, but our thinking process, we got to be careful on what we mean by each step. And we have to also be careful what was meant when we were doing our calculus here. And so what I'm really trying to say is, I am going to take an infinitely thin hoop. And as you pointed out, this is really not an infinitely thin hoop. Since an infinitely thin, the mass would really be 0. But in terms of calculus then, what does this become? Well, there's the beauty of it, right? There is the limit of the Riemann sum. There is my integral. Integral of what? And I guess what I'm really after is d what? What would go here? Well, what's going to 0? Right? Isn't the thing that goes to 0 the important piece of what is infinitesimally thin? So it's not a dr. I'm not saying the radius of the hoop is going to 0. Now don't get me wrong, and I think this is where it gets confusing. I'm going to add up a bunch of hoops. Isn't one of the hoops 0 radius? But obviously, when I start adding them up, and particularly when I get to the last hoop out there. The last hoop does not have a radius of 0. The last hoop has a radius of what I'll call the whole radius. So this is not a dr. This is a dm. And this happens to be then times the radius of that particular hoop. But this integral is a little bit harder. Can I take that r and pull it in front of the integral? No. Because as I'm adding up these hoops, the radius of each one is getting bigger and bigger and bigger. And so somehow I got to connect these together as I add them up. And again, that's where I think the math is a little bit harder. But again, if we make sure, I think if we read the math, we can come up with this answer. It won't be too hard. We have an integral. But it's not an integral like you might have seen. Maybe I better leave that there. It's not an integral like you saw in your math 150 or you're seeing now in your 160 class where, hey, let's take the integral of the inverse arctangent of the natural log raised to a power of 85. You know? And you've done and are doing some really hard integrals and learning a lot of good techniques like integration by parts and partial sums and all those techniques. This is not one of those integrals. This is a hard one, but it's a hard one, I think, more from the understanding of reading the math. So let's keep going. Are these connected in any way? The mass of an infinitesimally small hoop and a radius. Well, maybe I'll draw another picture over here. Here's this hoop. Go around a circle. Okay. It's really, really thin. It might have a thickness of what you might call dr. Fair enough? Now, don't confuse that with a radius of r. Now over here I have r, not dr. But I think you would agree that the mass is related to the dr. In fact, let me throw this word density out here. What's density? And maybe I should say mass density. Isn't mass density how much mass you have per volume? The kind of the standard symbol we like to use for mass density is rho. We saw it a little bit in the last chapter. I know we saw it kind of in chapter 1, but it's really going to play a big role now. What is the mass density? Well, it's mass per volume. Well, what mass, what volume?
Pi dr.
Okay, so you're getting the idea, good. Is that if I wanted to get this mass density, I mean, one thing is I could take the whole mass and divide it by the whole volume. On the other hand, I could take just a cutout ring of it and take the mass of that ring and also divide it by the volume of that ring. Here's what I mean by that. Here's our two options. The density can be the whole mass. So I'll put mass of disk. And if I did that, I would need to divide then by volume of disk. But that's not the only option, right? The nice thing about density, or maybe I should say uniform density, so if this thing has the same density everywhere, I can take a mass of a hoop. The hoop being, this kind of circular cutout. And then I would have to divide it by the volume of the hoop. And let's do both of those. Both of those will be very useful. This one will actually be useful right now. Because if I were to say, what is the mass of an infinitesimally small hoop, that would be this. That is what that meant right there, right? So I could write this as dm of hoop, right there. And what would be the volume of this hoop? And I guess I've only done kind of a two-dimensional view of it. But if I were to get the volume of this, and maybe I shouldn't say this, because it's really the volume of a hoop, wouldn't it be the circumference times the thickness times the width? And so my volume of a disk would be 2 pi r for that hoop. So there's the circumference. If I said this thing had a thickness of t, then I'll put a little t for the thickness. So I've got circumference, I've got thickness, and I've got width. That would be the dr for that particular ring. Whoops, I've been using the word hoop. Hoop. Let me put hoop. So what that really means then is dm, the mass of a hoop, is the density times all that factor. And so there's my 2 pi, there's my r of my hoop, there's my thickness, there's the dr of my hoop. And that's exactly what I was looking for when I asked this question. Aren't these two related? Is the mass of the hoop related to the radius of the hoop? Oh, absolutely. Right? And there it is. So if I were to take this equation with this additional information, and I'm just going to go ahead and erase that one, keep going here, then I would have an integral that, let's see, is the r squared of the hoop times the mass of the hoop. Well, the mass of the hoop, as we just said, is density times 2 pi times r of the hoop times the thickness times the dr of the hoop. So there's a lot of steps there, but it's also a lot of steps that are looking at the physical picture. I'm doing the integral more by understanding what each term means here. But the nice thing about that is I have now changed it to an integral that I can actually do, because I needed to know how these two were connected together, right? How is dm related to dr? And I found it. Now I found it right here from the density in geometry. That was the big step. And of course now you can see that I have things that don't change when you add them up. So the density I can pull out in front. The 2 pi I can pull out in front. The thickness I can pull out in front. And so I'm left with r cubed of the hoop dr. And that's probably the hardest part of this chapter, and even I would say this semester here, is looking at that picture here and saying, all right, I have now changed what was a summation into an integral, and it was an integral, which is a bunch of hoops, and once I get a bunch of hoops, I add a bunch of hoops, which I changed to an integral, and then I have to change those to the same term, and now I have it. Because now they're all dr's, and the hoops are going to go from 0 to, and I'll put r, but now I better put r of the disk. And again, it can get a little confusing because I got the same symbol up there for capital R, but I'm just running out of R's. I've already used a lowercase r, and now I've used an uppercase R, and I need another R. And so I'll just make it clear that this is the radius of the disk. And so coming back to our picture, here's what I'm saying. I am going to start at a small radius of 0 and keep getting bigger and bigger and bigger. In your earlier question, that would be a perfect answer. I could start with a radius that was not 0. I could call it the inner radius and then add up to the outer radius. But now it's a real easy integral to do. And so this was my comment earlier that you're not going to have to do a hard integral. We seldom in this class do a hard integral in the actual integral itself. The hard part is getting to the integral. It's like right here, knowing that I'm supposed to convert it into an integral. And notice what I'm supposed to convert the dm to a dr. That's usually the hard part. It's more about reading the math than actually doing the math. Because once I do this, this just becomes r to the 4th over 4 and evaluated from the radius of the disk to 0. And there's probably one more step worth taking. It comes back to the beginning. I kind of threw this new symbol out here, density, to kind of help me get through the problem. Let's get rid of it before we finish it. And we can write the density as the total mass of the disk divided by the total volume of the disk. Well, what is the total volume of this disk? Well, pi r squared would be the area of the disk, and then multiplied by the thickness would then be the total volume of it. So if I put that into here, I will get mass of the disk divided by pi r of the disk squared times the thickness, then times the 2 pi thickness, then times r to the 4th of the disk. And now a bunch of things simplify. For example, the pi's go away, the t's go away. Oh, I forgot my 4. Sorry about that. The 2 cancels with that 4, giving me a 2 downstairs. 2 of these cancel with 2 of those. And so when it's all said and done, I get an equation that looks something like this. And it has the mass of the disk, it has the whole radius of the disk, but it's got a prefactor in front. And in this case, it's a 1/2. And if you stand back and give it some thought, you go, okay, well that kind of makes sense then. There is a prefactor of 1/2. Because remember the hoop. The hoop had all the radius, or all the mass at a given radius. And so we just came up with mr squared. But the disk, or the cylinder, some of its mass is on the inside, some of it is on the outside or towards the end. So it's kind of like 1/2 would be kind of a nice average. Yep. And so the overall effect is as if all the mass is halfway. And I guess I should say halfway squared, so it's a little more complicated than that. But it does set up this nice equation. I'll put a box around it and say, okay, there is the moment of inertia of a cylinder. And so I had a cylinder earlier on here when I was rotating it. Well, I know that can be a little bit hard. So How about we do something like a rod? We spin a rod. How easy or hard is it to spin a rod? What's the moment of inertia of a rod? Well, maybe I'll clear these round objects off the board. Let's go to just a straight rod here. And my meter stick looks, suppose, a little bit like this in 3 dimensions, meaning that it has a length. And I know it's a meter stick, so I know it's 1 meter long, but for the sake of discussion, let's more generalize it and just say it's a rod of length L. Okay, and so I have a rod of length L. It, of course, is going to have some kind of height associated with it. Let me call that H. It's going to also have some kind of thickness associated with it. So let me call that T again for thickness. But let's go through the same thing. What is the I for a rod? Could we add them all together? Wouldn't it be a sum of MI/RI squared? Now there's something about this rod I want to make sure you really see here. Is what does this R mean in the summation again? From what to what? It's a distance, so it's got to measure 2 things, right? From what to what? What is this R?
Center of mass.
No. So this is adding up a bunch of chunks of mass, right? This R is from the rotational axis to that chunk of mass. Here's why I say that. Do you think I would get the same value if I took this rod and, like I have it set up right there, I've got it labeled from the center? What if I were to spin it a little differently? Instead of its center, what if I were to spin it around its end point? Do you think that's going to come out to be the same thing? No. Right? And so, what axis you spin it around is very important here. So maybe I should have been more clear over here. What did we just say about this hoop? Yeah, this was about its center, wasn't it? And isn't that the same thing we got for the disk? This was the eye of the disk, but it was about its center. And I didn't make a big deal of it at that time because we had enough to learn already. But I need to come back and emphasize that when you say, what is the moment of inertia, you have to, in addition to say, what is the shape of the object? A hoop, a cylinder, a rod. You also need to be saying it's about what point. Because you will get a different number if you do it around its center or around its end point. And I think we should do the center first, but then I think we should get off of center. In fact, we should even do the hoop and the disc off center. So instead of having a nice little hoop that spins around its center, we could put the hoop and have it spin around some point that is not its center. and its moment of inertia is different. And we need to know that. How is it different in order to solve these problems about energy? And so, like I said, this moment of inertia, we're spending a long time on it. It is a hard, both conceptual concept and mathematical concept of calculating it. All right, well, I'll come back over to here, as I said. Let's do this rod about its center. And I'll do the same thing we did for the hoop and for the disk. Let's take the limit as something goes to 0, and that something will be the individual pieces. What I'll do is I will take a chunk out of here and another chunk and another chunk and another chunk. And let me draw too many, because I think it'll just make the picture look cluttered. But I think you see the idea that I am going to chop this meter stick in, and let me not call it a meter stick anymore. Let me just call it a rod. I'm going to take this rod, I'm going to put it at its center right there, and I'm going to try and figure out how much energy it has when it's spinning. And that would mean I need to know its moment of inertia. So I got to add that all together. And in this case, it's spinning around its center. Soon, I will move it off center. Now, probably about as far as I can move it off center and keep it balanced. But it could be spinning off of center. What is it? Well, let me go back to center again. All right, so there's center. And so there's my spin. But I'm hopefully you're getting used to this now. Doesn't this just become an integral? This is the integral of what? R squared dm, right? What is going to 0? It's the mass. And so I chop the mass into little tiny pieces. And as I look up here, and the center one is in green, so I'll come back over here in green. And so if I measure everything, call this x equaling 0, then these little chunks of mass are at some position x. In other words, their position x is also their radius. Now I'll go back. What does this radius mean again? Distance. Distance of what? Distance from the rotational point to that little chunk of mass. And so this would become an x squared. And then dm is the mass of that little chunk. It is not the mass of the whole rod. However, just like we did for the disk, whereas we were adding things together, we need to get those to the same variable. How is the mass related to the radius? And I claim that there is a connection here, and that connection is density again. We can look at density both ways. We can look at density as the whole mass. So I'll take mass of the whole rod divided by the volume of the whole rod. Now, if I do the volume of the whole rod, it has length L, it has height H, it has thickness T. So that is one way to think about the density. But it's not the only way. If I look at a little chunk over here, that little chunk has a width of dx. So I can write this as the m. So I'll do the little m to match this little m, right? The mass of the little chunk. And then I would divide it by the volume of that little chunk. And that volume of a little chunk would be its length, dx, its height, L, its thickness, T. Oops, I'm sorry, dm should go there. dm is the mass of a little chunk. And of course then with a little bit of algebra, I can then say, here's my dm, and it would equal to rho times h times t times dx. And so that is how I would convert in this integral a dm to a dx. It would be rho times h times t times a dx. Perfect. And I say perfect because look what I've just done. This is the magical step that once I've done and changed it to an integral, the hard part, I think anyways, is right here. How do I get the m to be an x or the x's to be m's? But I think it's better to change the m's to an x. And so there's my converting of an m into an x using this idea of density. And of course now I need to add them up. And of course looking at all these chunks, I've kind of drawn in my picture going from 0 out to the end of the rod, but I got to do this side also. So I'm going to put my limits of integration. The first position is a chunk of mass that would be way over here at a position of negative L over 2. And then I would take another chunk and another chunk and another chunk and eventually get to 0, but I wouldn't stop there. I'd keep adding up until I got to the other side. L over 2. And now I can actually do the integral. And as I said, these are simple integrals themselves in terms of the calculus. It is getting to this point, which involves the reading of the math, that is probably the hard part. So as I write this out, I'll pull density out in front, I'll pull height out in front, I'll pull thickness out in front, because every little chunk has the same height and the same thickness. And now I have this integral of x squared dx, which of course is x cubed over 3, and we need to evaluate it from minus L over 2 to a plus L over 2. And now as I put those in, I get density times the height times the thickness. Let me just put the 3 over here. So this would then be an L over 2 cubed minus a negative L over 2 cubed. Simplifying this, that is an L cubed over 8 minus a negative means I've got 2 of those. That 2 would go into here, and so it looks like I have a 1/12 times the density times the height times the thickness times L cubed. And so there would actually be doing the calculus. And then one last step, which might be the easiest one finally, is to remember that we kind of introduced density in here in order to actually do this integral. We needed a connection between the x's and the m's. So let's get rid of the density before we finish, and that's where we can think of the whole mass. So then I get a 1/12. The density is the mass of the rod divided by the whole length of the rod, its height and its thickness. Then I have height and thickness and L cubed. So things cancel off like height and thickness. Even one of the L's cancel off. And so when it's all said and done, I have what I was looking for here. What is the moment of inertia of a rod about its center? Right? Did you notice? A rod. I got to give it shape and about its center. It's both the shape and what point, because that's what the moment of inertia depends on. Depends on the mass and the distribution of that mass.
Wait, how did you get to the last step?
Are you talking about this step where I replace the density with that thing?
Okay.
Okay, yeah, and that's, I came back over here for, yeah. By the way, how would this problem have been different if we had done it by the orange one here? Rotation around its endpoint. Yeah, if I had done this in orange, I guess I would have started at 0 and gone to L. But other than that, it would be the same. And we could do that integral, but I'll show you something even better. Because that would not be hard to do off center. This is a lot harder off center. And this is harder still off center. But fortunately, there's a very easy way to get off center. So let me make it very clear. We will do all of our calculations around the center, and then we will apply what I'm about to show you. It's called the parallel axis theorem, to get to things that are off center. It's actually very easy to get them off center once you know they are on, or once you know its value on its center. It's why, if any of you've got a chance to look through chapter 10, you will see that in about the middle of the book somewhere here in this chapter, your author goes through a bunch of calculations of different shapes, and he lists them in a big table. We have done the disc that is solid and the hoop, or he actually calls it a cylindrical shell. So we've done that. We've also done the rod about its center. We have not done the sphere, and he does both a hollow sphere and a solid sphere. He does a plate. But all of these, with the exception of this one, are all done on center. Why? Because what I'm about to show you is a very powerful and easy trick once you see it. It's called the parallel axis theorem. It's usually much easier to calculate the moment of inertia around center and then do the parallel axis theorem if we are off center. So let's try this. Let's run through kind of the derivation of the parallel axis theorem. It's got some interesting points to see. Fortunately, the result is pretty straightforward. Now, getting there isn't quite so straightforward, so it's worth seeing. But the most important part really is the end result here. What am I going to do if I have something that is rotating off of center? So if I actually have this rod, instead of here, here. And I claim, instead of calculating it off center, calculate it on center, which by the way you don't have to ever do again, we just did it. So it's 1/12 ml squared. And then apply this next step. And so this next step, as I said, is called the parallel axis theorem. Let's see how he sets it up here. He gives kind of this picture here. He says, let's take an object, and just to make it kind of generalized, he gives this weird shape and says, all right, somewhere, probably right about here, is the center of mass of that object. And what we're trying to do is to get it to rotate, and so let's put, like this is a piece of plywood, let's put a little nail right there, and let's get it to spin off of its center of mass. And though maybe I should put here a parallel axis theorem, but like I said, the idea here is what are you going to do if you're not on its center. And so if you were calculating the moment of inertia off center, you would be adding up all the little chunks of mass as measured from that off-centered point. Now, I'll say it again, it's worth repeating here. What is meant in each of these terms? The m is the little chunk of mass. Let's just draw one up here. Let's say that little chunk of mass, mi. So r I is that. Ri is the distance to that little chunk of mass. Let's do it in vector notation. This will be a vector, but here's where the little trick comes into play. This will be the, what he calls, call it a d vector, and this he calls, let's call it an r prime vector, meaning that the actual position of the mass can be thought of as two steps. One step being how far is it from your rotational axis to the center? That's the d. I want to make it real clear what the d means, because that's going to be important at the end of this. And the other part then is from the center to that chunk of mass. Okay? Because what we really want to add up is this little r. But if we write it this way, mi, and we put in the d and the r prime, and maybe I should put r prime I, because as you add up all the different chunks of mass that make this object up, d is never going to change. D is that distance from this rotational axis that is off center to that point that is the center. And then wherever that center is, then that's why the r prime changes as well as the r. And then I'll square that. And when you do that, you will get something that looks like a d squared there, a mi, and then you'll get a 2dri, and I guess technically they're vectors with a dot product in them. And the last term would be the sum of mi ri squared. And so I've done nothing more than apply the FOIL, right? I've got a binomial and I square it. So I've got the first term squared, I got the last term squared, and I got the cross terms twice.
Those r's be r primes?
Oh, thank you. Yes, they should be. Those should be r primes. Well, I'm squaring it, so I don't need that vector symbol anymore. But here's the beauty of the parallel axis theorem. And again, we're back to what you've been seeing all day long. Don't just do the math here, read it. What does each term really mean? Because this is surprisingly easy. Doesn't look it on the surface, but it's amazingly easy. Let's start here. What would this simplify to? Well, d never changes. You can add up all the chunks of mass in here, but d is the distance from this new rotational axis you're trying to discover to the center. And so as you add up all the chunks, the r and the r prime are changing, but not the d. So factoring out the d, what does this mean to you? That's just the total mass, right? This is the sum of the individual chunks. And so let me write it as md squared, where the m is the mass of this entire object. Fair enough? That's what that one simplifies to. This one even simplifies better. Perhaps harder to see. What does that one come out to be? Maybe you'll see it better if I rearrange it. The 2 and the D are the same. So let me bring them in front of my summation and pull them out. And what's that? Isn't that the summation for the center of mass? Maybe I should remind us, isn't the position of the center of mass 1 over the total mass of the object, the sum of MI/RI? Add it up. That from our chapter 9? And so isn't this then right here, this part? Isn't this really the mass total of the object times the position of its center of mass? It gets even better. What is the position of the center of mass? Now, again, let's pause here. Let's read the math. Don't do the math here. Let's read it. What am I really saying here? I am saying this is then the location of the center of mass as measured from what reference point? Well, the R primes. Where is R prime? Well, R prime is the center of mass. So here's what that little calculation is saying. That little calculation is saying, put your origin at the center of mass, and then go through a long calculation to find where is the center of mass. And what are you going to get? The origin. You put it at the center of mass, right? Doesn't get any easier than that. 0. Easiest calculation I've ever done. All right? But again, it's not so much the math, it's the reading of the math. And you've been seeing that all day long, and you're going to see it all chapter long here. Is what does each of these steps mean? And so this is saying, where is the center of mass? As measured from putting your origin at the center of mass. Well, as soon as you say that, just a dead giveaway, right? Put your origin at the center of mass, calculate where the center of mass, what are you going to get? 0. And so that's a nice little calculation. And let's get to this last one. What's this one telling me? Doesn't that look like moment of inertia? As measured from where? The prime, right? As measured from the center of mass. So this is the moment of inertia as measured from its center of mass. So here's the grand conclusion. The grand conclusion here is you can get the moment of inertia off center if you first of all know it at its center of mass, and then just multiply by how far you're moving away from the center of mass. It's perfect. So I told you that the details in the calculation are kind of fun to go through. They're more about reading the math than doing the math. But when it's all said and done, we actually get a very easy and very powerful equation. What is the moment of inertia off center? Well, start by knowing it on center, and then get off center. Let's try this example. Let's take this rod and put it so that it rotates around its end. And in fact, let's not stop there. Let's put it so it rotates around its end and put a hoop and a disc on top of it so that they rotate around their edge of their rim. What's the moment of inertia of that contraption? And now I think you're finally seeing what I've kind of been built up to for the last hour and a half is, could I get the moment of inertia of any crazy shape on an airplane that has wings that needs to do a barrel roll? Couldn't the wings be thought of as rods moved out from its end, added up? Couldn't the fuselage be thought of a cylinder that then rotates? The tail, maybe a bunch of other rods added up. I can now do any shape you want, and we will get some hard shapes. And that's what's going to make this weekend's homework a long homework, is looking at that shape, getting that physical picture. But let's try this shape. This shape would look something along this line. I'll start with the general concept of, hey, I want to find the moment of inertia of some crazy shape. So I would be the summation of MI/RI squared, right? But in my case, when I go to add up all the little chunks of mass, aren't those chunks of mass really in three categories? One category being a rod, another one being a hoop, and another one being a disk. And so I'm going to break that into the summation of MI/RI squared for the parts that make up the rod. And then I will break that into a summation for the parts that make up the hoop. And then I will do a summation that are the parts that make up the disk. That's just really a long way of saying, if you want to know the moment of inertia of a complicated shape, break that complicated shape into pieces you know. Rods, and in this case, hoops and discs. That table had spheres and plates. And so actually the plate would be a good one to actually represent maybe the tail and the wings on the airplane. But if I took a bunch of rods and added them together, that would give me a plate. So that's how the author gets the plate. And we're out of time to do more of them. We better move on here. But this is really the hard part. So add it together. I like to put it this way. The I total is nothing more than the sum of the I's of the individual pieces. Okay? That's what I'm trying to illustrate here. Take the individual pieces. And in my case, I've got 3 individual pieces. I got a rod, I got a hoop, and I got a disc. Okay? I'll add them together. So let's look at the rod for a moment. Could I get the moment of inertia of the rod? Well, yes. Didn't we work it out? It's still on the board, actually. Isn't it 1/12? Careful. What's the 1/12? About its center. Is this rotating around its center? No. So how do we get off center? Parallel axis theorem. So for me to find the rod, I would do this. I would say it is 1/12 ml squared plus m, and let me put rod. And how far am I moving off center? Okay, d. What would d be in this case, though? Yeah, half a L, right? Half the length of the rod. So I'm going from the center all the way to the end. So I'm going to put an L over 2 and square it. So that's my capital D in this. And that's why we went through this derivation. What is capital D? Capital D is how far did you move from the center? And so now I have the whole piece from the rod. Let's go to the hoop. We did the hoop earlier, right? Do you remember what we got for the hoop? M for the hoop, radius of the hoop squared. Yep. But that was about its center. Is that what I have going on here? No. It's not rotating about its center. It's been shifted over by how much? Its radius. So I would have M of the hoop times the radius of the hoop squared. And so that would be my moment of inertia of the hoop. How about the disc? Right, and so the disc was this. But again, I should emphasize that was about its center. And is that what we have in this problem? No. How far did I move off of center? Again, radius. Maybe I should have done something different between the disc and the hoop. But I can go M of the disc times the radius of the disc squared. And so there's the parallel axis theorem applied to each of them. And so again, hopefully it fits what I was saying. We're going to just calculate what they are around their centers, and then from that we can get off of center. And so that's why your author makes that big long table and says, look, this is the table. And like I said, I didn't do the spheres for you, but you know, I think there's a problem or two you have on the homework that has a big basketball. And a basketball, if you don't know, is hollow on the inside. It has compressed air, but it's not the thick rubber. Or maybe it's a soccer ball, but they want you to use the shell. Where there's another problem, I think they have a baseball. And so it's solid all the way through. So use the other one. And sometimes they're on center and sometimes they're off center. If we simplify this, a 1/12 and a quarter make a third. So that's a 1/3 mass of rod, length of rod squared. The hoop, that's a 1 and a 1, so that makes a 2 mass of hoop, radius squared of hoop. For the disc, looks like we have a 1 1/2, so that's 3/2 mass of disc times radius squared of disc. And actually, in my case, the mass of the disc and the hoop are the same and the radius are the same, so I could even simplify that. But I'll leave that alone just because that just happens to be the case for this one. But I wanted to kind of show in your notes that I've added the 3 objects, and each object I've included the off-center part of that. And if you see that, then there's going to be a piece of cake. You're going to sit down with the homework and you'll probably finish it in like 40 hours. I mean, no problem. All right? And so that's the moment of inertia. Oh, good. I think I saved just enough time to keep going along these lines because, as I said, I wanted to spend a lot of time, and I did, maybe even too much, really talking about this moment of inertia. I think the concept of it is hard, let alone the math behind it is hard. But let's keep going here. Let's do something along these lines. Here I have something that can spin. It's almost a disc. It looks like the wood on top is a disc. It looks like it gets a little more complicated when I include what's underneath, kind of this cone-shaped pulley system. So I won't worry exactly about what its shape is. But let's talk a little bit more about getting it to rotate. I mean, to get it to rotate, I would have to push on it, right? Uh-oh. Something broke. But where I push, does it matter? How I push, does it matter? I mean, what if I push right there? What if I push right there? So, doesn't where I push and what angle matter? Let's look at this door for a moment. You've probably seen people walking out the door. Let's see, this one is actually locked for some reason. But I'll put my foot here so it can't lock all the way here. But let's say I go to open the door. Do I push here to open the door? Or do I push here to open the door? Does it matter where I push? Does it matter what direction I push? I mean, what if I were to push this way? And so you see, I'm being a little silly here, but I am trying to point out, again, rotation is a little more complicated than translation. Because when we've talked about translation, we just said, give it a push. But as you'll see here, how you push, where you push, does matter. And fortunately, we can run through Newton's second law, and we will have Newton's second law of rotation, just like we had Newton's second law of translation. Let's put an object on here. I happen to have a disc-shaped object, so I will draw a disc-shaped object. But I'm going to leave it more general. It may not be as simple as a round object, but let's just say that there's some point right here, which is some distance away, call it r, and I apply a force. Now, here's what's nice about that force, is couldn't that force be thought of as what I will call the force tangential and the force radial? And the reason I draw those on there is when I go to push on this object, isn't it the tangential part that makes it turn? What does the radial part do? I mean, if I were to grab this and pull it radially, it doesn't make it turn, does it? Now, does it make it translate? Yeah. All right, so I'm not trying to change what we've already done in the past chapters, that the radial part is important, but it is not important when it comes to rotation. The only part that's important when it comes to rotation is the tangential part. So if I were to put this on the board, let's just say this little piece right there, let's call it m sub I, and if I apply Newton's second law, I would say that the tangential force is equal to m times A. I'm going to put a little subscript there saying, look, this is just for that little chunk of mass. Now, don't get me wrong. I know that all these chunks of mass are connected together. But just for a moment, if we were to say they're not hooked together, then I would say this force, but only the tangential part of the force, would then make it rotate. Let's keep going with this. Mi. This right here is the translational acceleration. Let me change it to a rotational acceleration and the radius. You might remember Monday we worked out the connection between them. Let me rearrange it just a little bit. I think now maybe you see where I'm going with this. What if I multiplied both sides by r? And then I said, let's apply this to every single point on that object. So there may or may not be another force on that piece. There may or may not be another force on that piece. There may or may not be another force on that piece. If there's not a force, then when I add up all the forces on the other pieces, these side would be 0. But there's definitely a mass there. And so if I take this summation of all the pieces, maybe now you're beginning to see it. What do you get over here on this side? What's this? Isn't this I alpha? Maybe it's worth putting in this chart now. When we did translational motion, we said that the net force is equal to mass times acceleration. What would be the equivalent of mass? Moment of inertia. What would be the equivalent of translational acceleration? Rotational acceleration. And so we're getting Newton's second law again. Now, I would call this Newton's second law of rotation as opposed to Newton's second law of translation. But this is the equivalent of the chapters 5 and 6 that we did. We did it for translation. We need to finish up this chapter and talk about Newton's second law of rotation. This right here, and I'll leave it as a summation and keep going. Let me write it this way. Here will be Ri. Here is F. Now remember, this was the amount of force that is tangential. So let's do this. If this is the radial direction, and this is the force, let's call the angle between them theta. So the tangential piece would be sine theta. This is a long way of getting to a new word here. And though I say new word, I know you saw it in Physics 102. We're going to call this the torque on the object. And so when we talked about objects moving, they were moved because of a force. So now when we talk about an object rotating, we're going to call it a torque. And probably not a surprise then that the symbol we will use for torque is the Greek letter tau. So we're back to our Greek symbols. Anytime we do a rotation, with the exception of this I, we like to use the Greek lettering. And so we have this thing called torque. And of course, this then is representing the summation of all the torques. And so this would then be the net torque equals I alpha. And so finishing up this little chart here, this then would be net torque. And this is my way of coming to the end of the chapter and throwing out the last piece that we haven't done now that we've done so much on energy and inertia and the other stuff. This is torque. And so torque equals I alpha, just like force equals ma. Now, we probably should spend a little bit of time talking about torque. I think torque is also conceptually a little bit harder to understand. I do want to point out, notice torque is not just force. It is where you apply the force and how you apply the force. That is, at what angle are you applying the force. So torque is much more complicated than just force. Let me put it this way. If I walk over to that door to open it, I would apply what to open the door? A force? Does the door translate or does the door rotate? Rotates. So do I apply a force or do I apply a torque? All right. And so as we have our little discussion here, I want to start there. It's really semantics is the first step. Make sure we understand the meaning behind this idea. Forces do what? Forces make things accelerate. They make them translate. What do torques do? They make them rotate. And so as we have our discussions, if I come over here and I make this thing rotate, I have just given it a torque. To make it translate, didn't mean for it to go that far. I give it a force, right? So forces make them translate, torques make them rotate. I want to stop this. I apply a torque. And if you want to call it a negative torque, so be it. Okay, but I apply a torque. Okay, again, torques make things rotate or stop rotating. But forces make them translate. So step one here is, like I said, just semantics. We went through a lot of math, and I hopefully am showing here that torque is a much more complicated formula than just force. But it's also just an understanding, you'll see it in the vocabulary, is it torque or is it force? So coming over here to open this door, I would want to apply a torque to open the door. I need a certain amount of torque for the door to open. Now let's go a little deeper here. Let's look at torque. What is torque made out of? Do you see three factors here? Getting that door to open is not just force. It is force, it is where that force is being applied, and it is what direction is that force being applied. That's why every once in a while, I will watch a student leave, and they'll come over here and they'll go. Of course, this one's locked. But eventually, they'll apply enough torque to open the door. But in order to get enough torque, they needed an enormous amount of force because what happened here? The radius is small. And so again, more of this discussion I want to have. Torque is far more than force. It's not just semantics, although that's a big part of it too. But it is also distance involved here. And so most of you, I think, have learned that over the years, that when you walk up to a door, you don't push it near the hinge. You don't even push it in the middle. You push it over here. Because in order to get enough torque, you have used the advantage of the R as much as you could, and then you applied a force. And I've never seen this, but what angle do most people push the door? At 90 degrees. Now let's come back to the picture. What is our definition of angle? Between the R and the F. So if I come over here to the door, here's the hinge right here. So this is R going this way. So to get the most torque, which way do I push it? 90 degrees to the R. And like I said, most people got that figured out. They come and they push it this way. I've never seen anybody come to the door and push it that way or that way. But if I do push it that way or that way, what's my angle? Either 0 or 180. And what is the sine of 0 or 180? 0. So how much torque do I get? 0. So how much does the door open? 0. You can put all the force you want. It doesn't make it rotate. Your torque is still 0. Riding a bike, as well as driving a car, although a lot of our cars have a automatic transmission, and so we don't give much thought to it. But riding a bike, most bikes have a multiple gear system. And the chain comes around and is connected to one of these gears. And actually, I guess we've got to be able to change the gears, so we got a little derailer system here. All right. All right. But have you ever been riding a bike and hit a big hill? What do you do when you get to the big hill?
Shift down.
You shift down. Why?
Change the radius or something.
Yeah, it's easier to pedal, isn't it? Now, again, let me emphasize, to get up that hill, to make the wheel turn, you don't need force, you need torque. And torque is a combination of force and distance. And so in my picture here, this chain is on a big gear, as opposed to the chain could have gone around a little gear. That little gear means that the radius that you're applying your force is smaller, and you are going to get less torque on that smaller gear. And hence, in order to get the minimum amount of torque to pedal up, you've got to push a lot harder. And so if you don't mind pushing hard, then you leave it in what we call the high gear being small radius, and that means you can get up the hill, but to get enough torque, you got to put a lot of force. And so that means you either push hard with your legs, or you stand up, or you do a combination of both. You stand up, you grab the handlebars, you push, but you got to get enough torque. And you can get enough torque by having a lot of force in a small distance, or, as you said, you can put it in a lower gear. And in a lower gear, you don't need much force, but you still get lots of torque because you have a lot of distance. And so again, more of the same, just like pushing on this door, torque is far more than just a force. It is a force, yes, but it is also how much distance away and at what angle. I will tell you a little heads up here. Your author, probably because we're doing so much others in this chapter, I'm pretty sure every problem in this chapter gives you an angle of 90 degrees. He will change that as we get into the next chapters, and particularly chapter 12. So we'll build up to it, but one step at a time here. And so we'll talk about it now, but we'll keep it relatively simple, at least as simple as we can. And so like I said, torque is not an easy concept. It's both moment of inertia and torque, I think, are the hardest things for students to understand this semester. This little experiment that we had earlier that now has come apart illustrates torque, I think, well also. Let me put it back together. But when I put it back together, I want you to notice which pulley I'm wrapping it on. See how I have applied it to the bigger of the 4 pulleys that are underneath there? So when I hook up this small little weight, and I put these back, well, I'll only put 3 of the 4. So toss the other one over there. But if I put this up here and we watch it unwind, I would say that it is this string, the tension in this string, that is applying the force. Then it is the distance or the radius of that top pulley, which is the R. The string is coming off at 90 degrees, so the sine of 90 degrees, which is 1, that's the torque. What do you think might happen? Well, we should just watch it again. So watch it. Watch the rate at which it unwinds. But what do you think would happen if I then took that string and I put it on the smallest pulley down here? And I'll even put the same weight on here. So it's the same weight, but is it the same torque? More or less? It is less. And so hopefully what you will notice is, oh, you got it kind of twisted there. All right. But hopefully what you will notice is that the rate of acceleration is much less than it was when I was on the other pulley, even though the weight that I am hanging is the same. So again, my point being here is that torque is much more complicated than force. So it's not just we're giving you a new word that has to be something different with rotation and translation. It is a whole different but related concept. Again, maybe you'll see it in here. If I take this rod and I put a big weight on this side and a small weight on that side, and I hold them level and I let them go, doesn't it rotate? In this case, doesn't it rotate counterclockwise? So since it's a rotation, I am interested in torques, not force. Which one gave me a bigger torque?
Small weights.
Isn't it the smaller weight? Right? Because torque, and as I'm trying to say here, is not just force. It's force and distance. So I deliberately put the smaller weight further out. And if I was doing this mathematically, I would say, okay, what is the acceleration? The acceleration is the net torque divided by the moment of inertia. Well, we spent a long time on moment of inertia. But torque then, there would be a clockwise and a counterclockwise. Let's call it positive and a negative. See, we called clockwise positive. No, I'm sorry, counterclockwise positive. And we called clockwise negative. So I would say this. I would say that if I calculate the torque from this one, it's a negative torque. Then I would add that torque to it, which is a positive torque. Clearly it rotates in a positive direction, so I must have more of a positive torque than a negative torque. What do you think might happen if I moved the lighter weight in? That's probably a little too much. Right? Because I moved it in, I changed its torque. This one I didn't change. This one is a negative torque. This one is a positive torque. But I reduced it by changing its R value. And so now I end up with a net negative torque. So which way does it accelerate? In the negative direction. So again, I can apply Newton's second law for rotation just like I would do for translation. Is it possible to balance these? And of course, if they are balanced, it would mean that the acceleration is 0. And so that means the positive torque and the negative torque would have to be equal. And it does not mean that the weights have to be equal. The forces aren't equal. The torques are equal. And again, I've said that a lot. Keep emphasizing. This is not just force. It is force and distance. It is torque. And again, one of the hardest things. Well, to wrap up in the time we have left here, let me put all this stuff in the chart. So let's see. I have the analogy of Newton's second law right here. It is a net torque. Trying to say that torque is the same as force, so shouldn't there be some units for torque? What would be the units? Well, that would be in newtons. That would be in meters. So wouldn't it be a newton times a meter? Now, didn't we see that before, newton times meter? What do we call that? A joule, right? And it had to do with work and energy. Now, is this energy? No. So let's do this. Don't call it a joule. That can just confuse you and everybody else you're trying to communicate with. So, here's our general rule that yes, this is a newton times a meter, but it's not a joule. Okay? If I were to take a wrench and put it on a bolt and grab it right here and put a force right here, then from here to here is the R. Force times distance gives me my torque. Don't confuse that with energy. Isn't energy the distance it actually moved? So if I actually push the wrench and it moves a distance of d, then the work is force times distance. The torque is force times radius. You see the different d's? Torque and work are not the same thing. I agreed they both have distance in them, but they are different distances. All the more reason, when we go to talk about the units of torque, let's call it a newton times a meter. Never call it a joule. It is not the same thing. And that will help with our clarification. And of course, I think the last thing that needs to be put in this chart is the one I used in the derivation that says torque is all three of these factors. It is the radius, it is the force, and it is the sine of the angle between them. That's how you get the torque. And if you add them together, you get net torque. And if you divide that by moment of inertia, you get the angular acceleration. And those are the type of problems. I guess one last question. Those of you who are mechanically inclined and you use wrenches all the time, and you look in the little shop manual and you take the manifold off and you've got to tighten it back on, it'll often say tighten up to a torque of, not a force of, a torque of, and at least in the English system, what do they often say? Foot-pounds, right? It'll say tighten to say 45 foot-pounds. Notice the distance and the force. Foot being the distance and force being in pounds. We, of course, being a science class here, will do the metric system, so we'll have Newton meters, but it's still that same idea. It's how much torque, not how much force. Well, good luck on the problems. I didn't get a chance to do any